in data science, we need to use several tools. Each of them have their own internal memory format. And thus, about 80% of the CPU is wasted on serializing, deserializing. And we have also several functionalities in the tools that are implicated several times. So we need no overhead of communication in one memory format. And so we heard about the Apache Arrow. And finally, like any other mature technology, we are in the need for standardization. And although some efforts are now on the way, we need to have standard data formats, standard data protocols, architectures, especially if we want to exchange information and data between different entities and also between different applications. The AI has always relied also on the hardware in which it runs. The current renaissance which we have with deep networks has to do with the research in GPU. And so the manufacturers are also pursuing different type of hardware that we can use to run our systems. Some of them are based on biologically based, like the neuromorphic architectures, or we can also use quantum computing, which is another way of looking at it. And quantum cryptography, can also be an option for privacy and security. Whoops. Concerning regulation and ethics, there have been also some ideas, interesting ideas this morning. Privacy, it's important, and especially if we are going to save our data on the cloud, our capacity over that is somehow limited. So we need to work on new methodologies on this. Just because you can access the data, it doesn't mean it's ethical to do it. And also, sometimes what happens, and that's the thing I'm trying to show in that figure over there, is that, for example, as I read, more than 85% of the USA population can be uniquely identified by their zip code, birth date, and sex. So if we mix this open data with other ways in which we have private data, we might cross them and identify the specific persons, which is not something that we would like to do. In this sense, the European Union is elaborating a law that will come into force in next year, in May, and it will regulate the data privacy, data security concerns, and also the right for an explanation, as we heard this morning. USA is preparing also new laws, but they are following a different way. So we also need to invest in safety, because we need to show that our systems operate in a way that we can understand and we can trust. So all the money that we invest on this will be not only on the technical side, but also on the strategy and other types of operations. Well, the existence of big data has opened a gap between those entities that are rich in data and those that are poor in data. Most of the ones that are rich in data have that data for free. And for example, if you work in academia, which is my case, the problem is that most of the time we don't have that data to work with on our own. We need to work with companies that own the data. So we will work for it. And when you elaborate your algorithm and you need to test it, and then you would like to publish your results because then every other researcher can benefit from it. What happens is that most journals ask you to share your algorithm, which is perfectly fine, but they ask you also to share your data. And that's for the reproducibility reasons, and that's a problem. Normally, because of confidentiality reasons, you have signed an agreement on that. In that sense, I think it's very important the ideas of that are on this document that I put the link down there, because they propose to have something, a place in which we can share public big data sets, and we can have the same kind of environment to try our algorithms, the same way that other repositories are, like the UC machine learning or something like this. And this, I think, is important, so all the researchers of the world can test the algorithms that they are working with. Many of the problems in data science come because we are working in the real world, and this has a lot of colors, flavors, shapes, etc. So we have several points to discuss. For example, we have high dimensionality data. We have data that's big not only in the number of samples, but also in features. And sometimes these data sets are enormous in features, but small in samples. And this causes your algorithms to generalize not very well. We have sparse data. That's the kind of thing that happens, for example, in recommender systems. A few users have rate a few items, and you need to recommend new items to new users. We have heterogeneous data that come from many different sources. You have missing data. This is quite frequent. Sometimes it's really not missing, it's just that you didn't think it was important to measure that, and then some moment in life you realize it's important, so you miss the previous one. In clinical studies, it's quite frequent, because the tests that we have now were not available some years ago, or because some of the data is from questionnaires and the patients didn't want to answer some of them. Of course, we have noisy data. We have untrustworthy data of any kind. Adversarial data is very important. This is data which has been modified very slightly with the aim of having your algorithm to misclassify, for example, and it's very difficult to detect. In fact, this is a hotline, and this year Google Brain has made a competition in the NIPS workshop on adversarial attack and defense. This is important for machine learning because our discipline has the value that the exploitation of the results give to it. And we are lagging behind in some areas, like the visualization of clusters, the situations in which patterns change, data drift, bias data also. Next talk will be on quality versus quantity data. This is a link to another talk that we have about what happens when you acquire data that's already biased from the origin. So you don't have a real representation of the world. You have a representation of the world which is biased, so towards part of it. And we need to do more work on feature engineering. In fact, tomorrow there is a talk also on feature selection and its challenge, regression, anomaly detection, which is something that in research has been going on and out, and in my opinion is very interesting nowadays, because more and more we need to detect what we don't know, that we don't know. We don't know which patterns are anomalous, when are they going to appear, how do they look, etc. Scalable transfer learning is important. Data visualization and integration, for example, for data visualization, feature selection can be used. I'm going to, whoops. Okay, I'm going to tell you a little bit about feature selection. Well, feature engineering is supposed to tell you which of the features of a data set are important. Most of the platforms that I know for machine learning in the Spark or in Flink or in any other platform do have feature extraction algorithms that tells you, that gives you a reduced number of features, but these are not the original ones. These are a dimensionality reduction with new features that are not the original. So you lack the possibility of direct explanation, which is important for AI systems, in my opinion. And I don't know of any platform that has feature selection algorithms inside. Also, more and more, we are having the need to have distributed feature selection algorithms because you have different sides of your company and you want to learn in all of them and then join the results, perhaps, or you have different hospitals in your country and you want to learn locally, but then you want to join the results already, and also you have problems if in these situations you have missing data, unbalanced data, heterogeneous data. Just to show you a couple of things on distributed learning. Well, if this thing allow me, yeps. Having problems. Here, oops, here. Just to show it's not easy, this is a graphic in which we are showing an artificial data set. It's not a big one, it's a small one, in which we have 1,000 features and 1,000 nodes. And we know the importance that they have, so we rank them using one node, centralized environment, and we rank them using distribution feature selection algorithm. And we compare both rankings, see if they both do the same. With using this index and DCG. If both are equal, we obtain the same result. Note that even with a high number of features per node, I don't know, 800, for example, you don't obtain equal ranking even using a lot of nodes, like another 800. You only obtain the yellowest part of it. In that part, they are equal. But if you do that, you have 1,000 features per node in 1,000 nodes. So what about the distribution part, which is the advantage of the situation? So to do this is not easy. Things that happens also with missing data. Normally, when you have missing data, what you do is you just ignore it. Let's throw the missing part of it. Or you decide to impute because you have a high percentage of missing data and you need to treat it. So what is normally done is you apply some imputation algorithm, reconstruct the data, and then you operate with it. This is just a graphical, we are working on this, but I'm showing you just a very graphical example. So we can see what happens. This is a data set, it's called MNIST, and as you see, it's the one that we have at the left. It's a digit, in this case a 9, 256 relevant features in an image, which is a little more than 500 pixels. The figure just behind that 9 is an image that we have done with control features. That means all of them are either irrelevant, the one in white, or redundant, the ones with gray or dark colors. Then we simulate missing data. That's what we assess there, using one of the ways of doing it, missing at random, example, 20% in both images. If we go and do imputation, I put there 2 of the most common algorithms. One is using the median, as you can see, for both images, and the one in the right is using SVD, which is a more powerful imputation algorithm. As you can see, using SVD, the reconstruction seems to be better we can differentiate the 9 clearly, while with the median, perhaps we can mistake this 9 with a 4. So far so good, but what happens if you then are going to do feature selection? See, we have a problem. If we use the original image and the points in blue are the ones retrieved by the feature selection algorithm, you see all of them are in the original image. If we force the algorithm to select more than the 256, because in a real situation you don't know how much do you need, then some of them are on the control image, which is no good because we know they are redundant. And we have more of the feature selection algorithm also recovers parts of the original image, which are clearly relevant. But if you go to the median imputation, the situation is quite similar. Although we have more blue points if we force the algorithm to retrieve around 500 features. But see, if we use the SVD imputation, just for the 200 features, there are some blue points already in the control image. And much more is the case, much worse, when we force the algorithm to select more, 500. All of them are even in the irrelevant part of both images. So this is important because we are affecting the discovery, introducing false negative and false positive points, which is something that we need to avoid. Oops, no, more. Size matters. So what happens, yeah, we are talking about big data, but what's big? Something might be big if you are small. For example, if with the quantity of wearables that we are having nowadays, something that's small for a mainframe is big for our smartwatch. If you want to calculate with it, perhaps you need to not use the full precision, 64 bits. What if you would like to make feature selection with a smaller number of bits? Well, this is some of the things that we are doing with an algorithm, with a feature selection algorithm based on mutual information. As you can see, the results are similar, just using 8 bits. So we can do it that way, and this is important. I'm almost running out of time, but not out of transparency, so I'll try to be quick. Scalability is something important, and in my opinion, we are looking at it only from the point of view that we are dealing with huge amounts of data, so we need to scale. But we should take into account scalability as an intrinsic characteristic of our methods. So we need to develop methodologies that assure scalability as just something that comes with your algorithm. And this is going to be important if you are having networks of AI systems, which will probably arrive very soon, because we cannot rely on a single AI system to manage very complex problems. And perhaps one of the elements of the network is a human. So we need to work on methodologies that take into account, we need to revisit the old multi-agent ideas. So we need new coordination mechanisms, communication mechanism, planification, etc. Privacy preserving is very important also, and sometimes our algorithms are not taking this into account. We need models that can learn already under privacy and anonymity constraints. For that, one option is to share parameter values, but not data. This is the image of an algorithm that we have developed at my research group. There is the journal in which we are going to publish it. And it's an anomaly detection algorithm which works using a distributed convex Hull approach. And we communicate in the network values of the parameters of the models, but never data. Another way of working is using aggregated data. In that case, you need to check your accuracy and if private data reconstruction is possible or not. Learning to learn is important. If I ask you, Which characteristics of intelligence are interesting? Probably versatility is one of it. Our systems work well in narrow niche situations, but not in a general situation. We need to learn most of the times from scratch if we are using artificial intelligence. Well, one way of, this is one of a picture which I think reflects the situation. It's the monitoring that the journal Spectrum does about diagnosing in medicine. As you can see, humans clearly win in general diagnosis, but perhaps we don't need to confront this from the point of view who wins, who loses. Oops. Another way of looking at it is the thing that Paco Nathan told us this morning, maintaining a human in the loop. And for doing this, because it can assist, for example, you can see in this image, using an algorithm can reduce the error of pathologies to almost zero. But for this, we need to work also on methodologies that develop new ways of interacting with humans and of communication between humans and machines. Explainability is something very important. Some of the present algorithms that are the kings of the situation, like deep learning, had limited explainability capacity, and of course we are not going perhaps now to have systems that can discuss of philosophy with us, but yes, we need to explain some situations in a way that's understandable by humans. And whoops, we have AI applications that are here already, like, like the robots there, public safety, etc. And we probably will assist to new applications that can help you to pass your transparencies. On education, for example, so we'll need to treat individuality, on healthcare, on low-resource communities, and on entertainment. And for example, these ones on entertainment are very well accepted, but it arises concerns on other disciplines like the social sciences because of the social risk of diminishing interpersonal interactions, something anticipated in the science fiction books. In this way, we will need to incorporate new professionals to artificial intelligence, probably lawyers, economists, social scientists, neurologists, and so on. And I have run already out of time a couple of minutes ago, just saying that employment and workplace is another important concern. Perhaps we need to discuss that we will have new employments and new ways of dealing or of interacting between humans and machine, and perhaps the humans will need to change our way of working in ways that we are not able to see now. Someone talked about this morning on the need for the universal basic income, something important, perhaps to alleviate this transition on the revolution, on the technological revolution that we are assisting now. This is one of the most important barriers to AI adoption, as you can see here. And finally, and very briefly, as I'm a woman, as you can see, I think that's important also that we need to try to attract also more talent, more women to our field, because we are in a very, very, very low percentage. 6% I think is not acceptable, because out there are 50% talented men and women, and we are not in the same, represented in the same percentage here. And that's all.
Thank you, Amparo.
Sorry because I'm late.
No, it's perfectly all right. Thank you. So I just speak on the very last point. Yes, I think you are right. I think from the point of view of the organization of this conference, we invited actually a higher percentage of keynote speakers like you, women, than the call for proposals had in terms of proportion. So yeah, I kind of agree that there is still a lot of to do to try to increase the awareness and how sexy these technologies can be for everybody, not only us men. Again, I don't see anything, but if there's any question for Amparo, please give a shout, don't be shy. Otherwise, you can always reach her at the lobby. Right, okay, so that's fantastic. So thank you very much, it's been a pleasure. Thank you, Amparo.
Thank you, Ruben.